Look up at the night sky, and what do you see? A scattering of stars, maybe a planet or two. But what if I told you there's an entire hidden universe pulsing just beyond your vision? A universe written not in the gentle glow of starlight, but in the searing, invisible language of gamma rays, the most energetic light in existence. These aren't just random flashes in the dark. They're cosmic fingerprints left behind by the most violent events the universe has to offer: collapsing stars, colliding black holes, explosions so powerful they outshine entire galaxies. Every burst is a clue, a piece of a puzzle that traces the universe's endless cycle of destruction and rebirth. Think about this for a moment. Every time you gaze at the stars, you're looking at light that's traveled millions, sometimes billions, of years to reach your eyes. But gamma rays, they carry stories from places where time and space bend to their limits, where matter is torn apart and forged anew. They're messengers from the edge of physics itself, whispering secrets about how the universe tears itself down only to rebuild again. And here's the thing, we're only just beginning to understand what they're telling us. This is the story of how gamma rays illuminate the blueprint of cosmic rebirth. From the cataclysmic deaths of massive stars to the mind-bending collisions of neutron stars, these high-energy bursts don't just signal an end. They mark the beginning of something new. Heavy elements like gold and platinum are born in these explosions, scattered across space to become the building blocks of future worlds. Black holes, often seen as cosmic destroyers, actually sculpt galaxies with their gamma-ray jets, shaping the universe on a scale we're only starting to grasp. By the time we're done, you'll never look at the night sky the same way again, because once you see the universe through the lens of gamma rays, you realize it's not just a static painting of stars, it's a living, breathing story of creation, written in the most powerful light there is. Gamma rays don't just appear out of nowhere, they're forged in the universe's most extreme environments, where the laws of physics are pushed to their limits. Picture a massive star dozens of times heavier than our Sun, reaching the end of its life. As it collapses under its own gravity, the core implodes in a supernova explosion so powerful it can outshine an entire galaxy for weeks. In that moment of cataclysmic destruction, temperatures soar to billions of degrees and atomic nuclei are ripped apart, unleashing a storm of gamma rays. This isn't just light, it's raw energy, a scream from the universe's most violent rebirths. But supernova aren't the only cosmic factories for gamma rays. When two neutron stars, the dense, city-sized remnants of dead stars, spiral into each other, their collision sends shockwaves through space-time. The impact is so intense that it warps matter into exotic forms, flinging out jets of gamma rays alongside gravitational waves. These mergers are cosmic alchemy labs where gold, platinum, and other heavy elements are forged in an instant. It's as if the universe takes destruction and turns it into creation, scattering the ingredients for future planets, and maybe even life across the cosmos. Then there are black holes, the ultimate cosmic devourers. As they feast on gas, dust, or even entire stars, the material doesn't just vanish. It spirals into an accretion disk, heated to unimaginable temperatures, and some of it gets blasted back out in jets traveling near the speed of light. These jets glow fiercely in gamma rays, acting like cosmic lighthouses visible across billions of light years. Far from being purely destructive, black holes are also cosmic recyclers, shaping galaxies and seeding the universe with energy. What makes gamma rays so special isn't just their energy, it's their ability to cut through the universe's clutter. Visible light gets absorbed or scattered by dust and gas, but gamma rays barrel straight through, carrying unfiltered information from the most distant and violent events. When scientists first detected them in the 1960s, it was like uncovering a hidden layer of reality. Suddenly, they could peer into the hearts of supernova, track the aftermath of neutron star collisions, and witness black holes in action, all through this invisible, high-energy light. These rays are more than just radiation, they're messengers from the edge of what's possible. Every burst carries clues about how matter behaves under extreme conditions, how elements are born, and how the universe constantly reinvents itself. To understand gamma rays is to understand the universe's blueprint, written in the most energetic language there is. Gamma-ray bursts are like the universe's most spectacular fireworks, blindingly bright, unimaginably powerful, and gone in the blink of an eye. In just a few seconds, a single burst can release more energy than our sun will emit in its entire 10 billion-year lifetime. That kind of raw power doesn't come from just anywhere. These flashes originate from some of the most extreme events in existence, stellar deaths so violent they rip apart the very fabric of space and time. There are two main types of gamma-ray bursts, each telling a different story of cosmic destruction and rebirth. The long bursts, lasting anywhere from 2 seconds to several minutes, are the final screams of massive stars collapsing into black holes. Imagine a star 20 to 30 times heavier than our sun, burning through its fuel in a fiery tantrum before its core implodes under its own weight. As the star's outer layers come crashing down, they rebound off the newly formed black hole, launching jets of plasma at nearly the speed of light. These jets punch through the dying star's remains, and where they break free, they unleash a torrent of gamma rays, an explosion visible halfway across the observable universe. Then there are the short bursts lasting less than 2 seconds and packing just as much punch. These come from a different kind of cosmic collision, neutron stars spiraling into each other in a deadly dance. When these ultra-dense remnants of dead stars finally merge, they don't just create a black hole. They send out shockwaves that forge gold, platinum, and other heavy elements in a single, spectacular flash. In 2017, astronomers witnessed one of these events for the first time, catching both the gamma-ray burst and the ripples in space-time it produced. That collision alone created enough gold to outweigh the Earth several times over, scattering precious metals into the cosmos like seeds for future solar systems. But the burst itself is only the beginning. What comes next is just as important, the afterglow. As the gamma rays fade, they leave behind a lingering fingerprint in X-rays, visible light, and radio waves. This afterglow acts like a cosmic crime scene, allowing scientists to piece together what happened. By studying its brightness, how quickly it fades, and the elements it leaves behind, astronomers can reconstruct the explosion's energy, the environment around it, and even the distant galaxy where it occurred. Some afterglows last for weeks, acting as beacons that guide telescopes to the exact spot where the universe just rewrote its own blueprint. What's truly mind-blowing is the role these bursts play in the grand scheme of things. Every time one goes off, it's not just an ending, it's a new beginning. The heavy elements forged in these explosions don't just vanish. They become part of interstellar clouds, eventually collapsing into new stars, new planets, and maybe even new life. The gold in your jewelry, the uranium in nuclear reactors, the platinum in catalytic converters, they all owe their existence to these cataclysmic events. Gamma-ray bursts are more than just distant flashes of light. They're the universe's way of recycling itself, turning destruction into creation on a scale we're only beginning to understand. And with every new burst we detect, we're not just watching a star die, we're witnessing the birth of something new. When a massive star reaches the end of its life, it doesn't simply burn out, it goes out with a bang so colossal it reshapes the fabric of space around it. A supernova explosion is nature's ultimate recycling program, tearing apart atoms with enough force to outshine entire galaxies for weeks. But what's left behind is just as fascinating as the explosion itself. The core of the star collapses into an unimaginably dense object, either a neutron star, where a sun's worth of mass is crammed into a city-sized sphere, or a black hole where gravity wins the ultimate battle against matter. These remnants don't just sit quietly in space, they become powerhouses of gamma-ray production. Neutron stars, especially the rapidly spinning ones called pulsars, act like cosmic lighthouses. Their intense magnetic fields whip charged particles around at nearly the speed of light, forcing them to release gamma rays in focused beams that sweep across the universe with every rotation. Some pulsars spin hundreds of times per second, turning them into precise cosmic clocks. Each pulse is a beacon of high-energy light, carrying information about the extreme physics at play on their surfaces. Black holes, on the other hand, are far from the dark voids they're often imagined to be. When they feed on nearby gas, dust, or even entire stars, the material doesn't just vanish beyond the event horizon. It forms a swirling, superheated disk around the black hole, glowing fiercely in X-rays and gamma rays. Some of this material gets funneled into jets that blast outward at nearly light speed, stretching for thousands of light years. These jets are so powerful they can reshape entire galaxies, heating interstellar gas and influencing where new stars can form. What's truly remarkable is how these processes tie into the larger story of cosmic rebirth. The same explosions that destroy stars also scatter heavy elements like iron, oxygen, and carbon into space ingredients that will one day become part of new stars, planets, and even life. The gamma rays produced in these events aren't just byproducts, they're signals that help us map this intricate cycle of destruction and creation. Without the violent deaths of stars, the universe as we know it wouldn't exist. This constant churn of matter and energy is what keeps the cosmos alive. Every gamma ray burst, every pulsar's flash, every jet from a feeding black hole is part of a grander narrative, one where endings are just the beginning of something new. Neutron star collisions are the universe's ultimate forges, where the heaviest elements are born in a blaze of light and fury. Picture two city-sized remnants of dead stars, each so dense that a single teaspoon of their material weighs as much as a mountain. Locked in a deadly spiral, they whip around each other hundreds of times per second, warping spacetime itself until finally they collide. The impact unleashes a kilonova, an explosion so intense it briefly outshines a million suns. But this isn't just a spectacle of destruction. It's a cosmic factory where the gold in your jewelry, the platinum in medical devices, and the uranium powering nuclear reactors are forged in the heart of the inferno. The groundbreaking moment came in 2017, when astronomers witnessed one of these events for the first time. WGW170817. After the gravitational waves it produced, this collision sent ripples through spacetime that were picked up by detectors here on Earth. Just 2 seconds later, a gamma ray burst flashed across the sky, a smoking gun linking the merger to the high-energy light. Telescopes around the world swiveled to catch the aftermath, revealing a glowing cloud of heavy elements expanding into space. The data was undeniable. Neutron star collisions are the universe's primary source of elements like gold and platinum, scattering them like cosmic treasure across the cosmos. What makes these mergers so special isn't just the elements they create, it's how they do it. In the chaotic seconds after impact, neutrons are ripped from the colliding stars and flung into the surrounding space. There, they're captured by atomic nuclei in a rapid-fire process called the R process, building heavier and heavier elements in a chain reaction. This alchemy happens nowhere else in nature, at least not on this scale. Supernova can produce some heavy elements, but neutron star collisions are the true masters, operating at temperatures and pressures so extreme they defy laboratory replication. The aftermath of these collisions is just as fascinating. The ejected material doesn't just disperse quietly, it forms intricate structures like glowing tendrils and bubbles as it expands into space. Over thousands of years, this debris will mix with interstellar gas, eventually becoming part of new stars and planets. Every time you hold a piece of gold, you're holding stardust forged in one of these cataclysmic events, a remnant of a neutron star's final moments. But the story doesn't end there. These collisions also produce gravitational waves, ripples in spacetime that carry information about the merger's dynamics. By studying these waves, scientists can measure the star's masses, their spin rates, even the shape of the spacetime warping around them. Combined with gamma-ray observations, this data paints a complete picture of the universe's most extreme recycling program. Neutron star collisions are more than just cosmic smash-ups, they're vital chapters in the story of cosmic rebirth. Without them, the universe would lack the heavy elements needed for planets, life, and even the technology we use to study them. Each merger is a reminder that destruction and creation are two sides of the same coin, woven into the fabric of the cosmos. At the heart of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole, an invisible titan with gravity so strong that not even light can escape. But here's the twist: these cosmic behemoths aren't just passive voids. They're some of the most powerful gamma-ray engines in the universe, capable of shaping entire galaxies with their energy. When a black hole feeds, it doesn't just swallow matter quietly. Gas, dust, and even entire stars spiral into an accretion disk, heated to millions of degrees until it glows brighter than all the stars in the galaxy combined. Some of this superheated material doesn't cross the event horizon instead. It gets funneled into twin jets that blast outward at nearly the speed of light, stretching across millions of light years. These jets are so energetic they emit gamma rays, visible across the cosmos like searchlights piercing the darkness. Take the black hole at the center of the galaxy Messier 87, famous for the first ever image of a black hole's shadow. Its jet stretches 5,000 light-years into space, a stream of particles accelerated to velocities we can barely comprehend. Similar jets have been spotted in galaxies billions of light-years away, their gamma-ray signatures revealing how black holes influence their surroundings. These aren't just random eruptions, they're cosmic feedback mechanisms, regulating star formation by heating interstellar gas or blasting it away entirely. In some cases, a black hole's jet can even trigger the birth of new stars by compressing nearby gas clouds, proving that destruction and creation are deeply intertwined. What's even more fascinating is the flickering behavior of some active black holes. Observations from telescopes like Fermi show that their gamma-ray output isn't steady, it flares unpredictably, sometimes doubling in brightness within hours. These flickers hint at chaotic feasting, like a cosmic strobe light flashing as the black hole devours clumps of matter. Scientists compare it to a poorly tuned engine, sputtering as it gulps down uneven fuel. Each flare carries clues about the black hole's appetite, the structure of its magnetic fields, and even the physics of spacetime near the event horizon. Far from being the universe's ultimate destroyers, supermassive black holes are architects of renewal. Their gamma-ray jets seed the cosmos with energy, redistribute matter, and sculpt galaxies into the structures we see today. Without them, the universe might lack the diversity of galaxies we observe, from spirals like our own to massive ellipticals gleaming with ancient stars. They remind us that even in the darkest corners of space, there's a hidden order, a balance between chaos and creation, powered by the invisible hand of gravity. Before Fermi launched into orbit, our view of the high-energy universe was like staring through a keyhole, glimpsing only fragments of gamma-ray mysteries. That all changed in 2008 when this revolutionary telescope opened its eyes to the cosmos, transforming our understanding of cosmic violence. Named after physicist Enrico Fermi, the spacecraft carries two cutting-edge instruments: the Large Area Telescope, which scans about a fifth of the sky every 3 hours, and the Gamma Ray Burst Monitor, always on alert for sudden flashes of energy. Together, they've built the most detailed map of the gamma-ray universe ever created, a dynamic tapestry of pulsars, black holes, and galaxies blazing with unimaginable power. What makes Fermi so extraordinary is its ability to capture gamma rays across an enormous energy range, from thousands to hundreds of billions of electron volts. To put that in perspective, visible light photons carry just 2 to 3 electron volts. Fermi detects particles with energies comparable to a fastball pitch, all packed into a single subatomic photon. This sensitivity has allowed it to spot over 5,000 distinct gamma-ray sources, rewriting textbooks in the process. Before Fermi, we knew of just 7 pulsars emitting gamma rays. Today, that number exceeds 300, each one a rapidly spinning neutron star beaming high-energy light like a cosmic lighthouse. Some of Fermi's most startling discoveries come from beyond our galaxy. It has mapped the gamma-ray fog emanating from distant blazars galaxies with supermassive black holes whose jets point directly at Earth. These jets flicker like cosmic strobe lights, their variability revealing how black holes feed and accelerate particles. In 2010, Fermi spotted a gamma-ray structure no one expected: 2 enormous bubbles stretching 25,000 light-years each, towering above and below the Milky Way's core. Dubbed the Fermi bubbles, these formations glow in high-energy light, possibly relics of an ancient black hole outburst that occurred millions of years ago. But Fermi's greatest value lies in its relentless monitoring. Unlike telescopes that focus on single targets, Fermi watches the entire sky continuously, catching transient events others might miss. When a gamma-ray burst erupts somewhere in the universe, Fermi's burst monitor often detects it first, triggering alerts to observatories worldwide. This rapid response system has allowed astronomers to study bursts in unprecedented detail, linking them to supernova and neutron star collisions. The telescope also tracks the sun's gamma-ray flares, helping scientists understand how our star accelerates particles during violent eruptions. Perhaps most intriguing are the mysteries Fermi has uncovered: signals that defy explanation. There's the gamma-ray excess at the Milky Way center, a glow that could hint at dark matter particles annihilating one another. Then there are the unexplained flashes from seemingly empty space, brief bursts with no obvious source. Each anomaly pushes scientists to rethink physics, probing whether these could be signs of new particles, exotic black hole behavior, or even phenomena we haven't yet imagined. Without Fermi, modern gamma-ray astronomy would be stumbling in the dark. Its data forms the foundation for thousands of research papers, fueling discoveries about cosmic rays, dark matter, and the extreme physics governing the universe. As it continues its mission, this unassuming satellite, no bigger than a compact car, remains our sharpest eye on the high-energy cosmos, revealing a universe far more dynamic and violent than we ever dreamed. Dark matter is the universe's greatest ghost story, an invisible presence that outnumbers ordinary matter 5 to 1, yet refuses to reveal itself. We know it's there because galaxies spin too fast to hold themselves together without it, and light bends around empty space as if something massive lurks unseen. But what if this cosmic phantom leaves fingerprints in gamma rays? Some theories propose that when dark matter particles collide, they annihilate in bursts of high-energy light. It's a tantalizing idea. The same mysterious substance shaping galaxies might also betray its secrets through the universe's most energetic radiation. The Fermi Gamma Ray Space Telescope has spent over a decade hunting for these elusive signals. Scientists focus on regions where dark matter should concentrate dwarf galaxies orbiting the Milky Way, which are rich in dark matter but poor in stars, reducing background noise. Galaxy clusters, massive gatherings of hundreds of galaxies bound by dark matter's gravity, are another prime target. If dark matter annihilates, these places should glow faintly in gamma rays with a distinct energy signature. Fermi has detected excess gamma rays in both locales, but the smoking gun remains just out of reach. The signals could be from known astrophysical processes, pulsars, black holes, or cosmic rays interacting with gas, or they could be our first glimpse of dark matter's hidden nature. One of the most intriguing puzzles comes from the Milky Way's heart. The galactic center emits far more gamma rays than expected, peaking at energies around 1 to 3 billion electron volts. Some researchers argue this excess matches predictions for certain dark matter particles called WIMP, weakly interacting massive particles. These hypothetical particles would annihilate in pairs, producing gamma rays at specific energies. Others point to alternative explanations, like undiscovered pulsars or ancient outbursts from the supermassive black hole Sagittarius, a star. The debate rages because the signal isn't sharp enough to confirm or rule out dark matter definitively. The stakes couldn't be higher. If dark matter truly produces gamma rays, it would revolutionize particle physics and cosmology. We might finally understand why galaxies formed the way they did, how the universe evolved its large-scale structure, and what makes up the bulk of matter in existence. But even if the current signals turn out to be astrophysical noise, the search has already pushed detector technology and data analysis to new heights. Every unexplained flicker forces scientists to refine their models, ruling out possibilities and inching closer to the truth. What makes this hunt so compelling is its sheer audacity. We're searching for something that doesn't emit, reflect, or absorb light by looking for the light it just might create under extraordinary circumstances. It's like trying to spot a shadow by the glow of its friction with the air. Yet the potential payoff justifies the effort. Unraveling dark matter wouldn't just solve a cosmic mystery, it would rewrite the story of how the universe builds and rebuilds itself. And gamma rays, those fleeting messengers from the abyss, might be the key to lifting the veil. Deep in the heart of our Milky Way, something strange is happening. A cosmic battle between matter and antimatter playing out in bursts of gamma rays. Astronomers call it the Great Annihilator, and its true identity remains one of the galaxy's most intriguing puzzles. Unlike most of the universe where matter dominates, this source produces a surprising amount of antimatter, specifically positrons, the antimatter counterpart to electrons. When these particles meet ordinary matter, they annihilate in flashes of gamma ray light, creating a signal so distinctive it stands out against the galactic backdrop. The mystery lies in what's generating these positrons. One leading theory points to a nearby neutron star with an unusually strong magnetic field, accelerating particles to energies where they spontaneously create matter-antimatter pairs. Another possibility is a small black hole, its gravitational pull tearing apart nearby stars and generating antimatter in the chaotic debris, but neither explanation fully fits the data. The Great Annihilator's gamma ray signature flickers unpredictably, sometimes flaring brightly before fading into near invisibility, as if it's toggling between power states. This erratic behavior defies the steady output expected from typical neutron stars or black holes, leaving scientists scrambling for alternatives. What makes this enigma so compelling is the sheer rarity of antimatter in the universe. The Big Bang should have created equal amounts of matter and antimatter, yet today, antimatter is vanishingly scarce, a cosmic imbalance that remains unexplained. The Great Annihilator offers a rare laboratory to study how antimatter behaves in the wild. Its gamma rays carry clues about the conditions that produce and sustain these exotic particles, hinting at physics beyond our current models. Some researchers speculate the source could be stranger still, perhaps a previously unknown type of compact object, like a quark star or a black hole with unique magnetic properties. Others wonder if we're seeing the aftermath of an ancient stellar collision, where the remnants continue to interact in unexpected ways. Every new observation adds another piece to the puzzle, but the full picture remains just out of reach. What's certain is that the Great Annihilator challenges our assumptions. In a universe where destruction often leads to creation, this gamma-ray source reminds us that even the most violent processes can illuminate new frontiers of physics. Whether it's a neutron star, a black hole, or something entirely unexpected, its story is still being written one gamma-ray flash at a time. Every gamma-ray tells a story, but some carry tales older than Earth itself, ancient light that's been traveling since the universe was a fraction of its current age. These high-energy photons are cosmic archaeologists, preserving snapshots of a time when galaxies were just beginning to assemble, and the first stars burned with a brilliance we can scarcely imagine. Unlike visible light, which gets scattered or absorbed over cosmic distances, gamma rays barrel through the void nearly untouched, delivering pristine messages from the universe's formative years. Take the gamma-ray bursts recorded by telescopes like Fermi. Some originate from galaxies so distant their light has taken over 13 billion years to reach us. That means we're witnessing explosions that occurred when the universe was less than 1 billion years old, a mere infant by cosmic standards. The bursts themselves are spectacular, but their afterglows are even more revealing. By analyzing the way this light interacts with the gas and dust between galaxies, astronomers can map the conditions of the early cosmos. They've discovered that the young universe was far more chaotic than today, with star-forming regions operating at breakneck speeds, churning out stellar nurseries at rates dwarfing anything in the modern Milky Way. One of the most surprising revelations is how quickly supermassive black holes appeared in this primordial era. Gamma rays from quasars, extremely luminous galaxies powered by voracious black holes, show that some of these monsters already weighed billions of suns when the universe was less than 1/10 of its current age. That shouldn't be possible under traditional models of black hole growth, forcing scientists to rethink how these giants form. Did they arise from collapsing clouds of primordial gas, or were they seeded by something even more exotic, like direct collapse black holes born in the aftermath of the Big Bang? The gamma rays don't answer every question, but they provide critical clues, narrowing down the possibilities. Then there's the cosmic dawn, the epoch when the first stars flickered to life, ending the universe's dark ages. Gamma rays help probe this transition indirectly. When massive early stars exploded as supernova, their gamma-ray emission ionized surrounding hydrogen, leaving markers in the intergalactic medium. By studying how these signals propagate, researchers can estimate when and where the first stellar generations emerged. It's like using the echo of a long-dead star to reconstruct the moment light first pierced the cosmic gloom. What's remarkable is how these ancient photons connect to the present. The elements forged in those early stars, carbon, oxygen, silicon, were blasted into space by gamma-ray bursts and supernova, later incorporated into planets like Earth. The same violent processes that shaped the young universe also set the stage for life. Every gamma ray from that era is a thread in a grand tapestry, linking the chaos of creation to the delicate balance we see today. Yet mysteries remain. Some gamma-ray signals from the early universe don't match any known sources, hinting at phenomena we've yet to discover. Perhaps stars made of dark matter, or black holes with properties alien to modern ones. Each anomaly is a reminder that the universe's adolescence was wilder and more inventive than our theories predict. And as telescopes grow more sensitive, we're poised to uncover even deeper layers of this cosmic coming-of-age story, written in the relentless glow of gamma-ray light. Some of the universe's brightest beacons aren't stars at all, they're blazars, galaxies so luminous they outshine entire star clusters, all thanks to a cosmic quirk of geometry. At their core lies a supermassive black hole, billions of times heavier than our Sun, devouring matter with such fury that it launches jets of plasma at nearly the speed of light. Normally, these jets would be just another feature in the cosmic landscape, but in blazars, they're aimed directly at Earth, turning these distant galaxies into searchlights piercing the darkness of space. The result, a torrent of gamma rays so intense it drowns out nearly everything else in the sky. What makes blazars truly fascinating is their volatility. Unlike steady cosmic lighthouses such as pulsars, blazars flicker unpredictably, flaring to blinding brightness before fading back into obscurity, sometimes within hours. These outbursts are like cosmic weather reports, signaling storms raging near the black hole's event horizon. When a clump of gas or a star strays too close, the black hole's immense gravity shreds it apart, heating the debris to billions of degrees and funneling it into the jets. The resulting gamma-ray flare carries fingerprints of the destruction, revealing details about the black hole's spin, the jet's magnetic fields, and even the physics of particle acceleration at energies far beyond anything achievable in labs on Earth. One of the most studied blazars, known as Mstirk 421, lies about 400 million light-years away. In 2012, it erupted with a gamma-ray flare so powerful, it temporarily became the brightest object in the high-energy sky. For a few days, it outshone the entire Milky Way in gamma rays, emitting more energy in a single outburst than our Sun will produce in its entire lifetime. Telescopes around the world scrambled to observe the event, capturing data that transformed our understanding of how black holes channel energy into these narrow, relativistic beams. But blazars aren't just celestial oddities, they're cosmic laboratories. Their jets act as natural particle accelerators, far more powerful than the Large Hadron Collider. Electrons and protons surf on shock waves within the jets, reaching energies that make them glow in gamma rays. By studying these processes, scientists can test theories about how matter behaves under extreme conditions, probing the limits of Einstein's relativity and quantum physics. Some blazar jets even exhibit bizarre behavior, like apparent motions faster than light, an illusion caused by particles racing toward us at angles just shy of light speed, warping our perception of time and distance. Perhaps the most humbling realization is how fleeting these glimpses are. The light from the brightest blazar flare might have traveled halfway across the observable universe before reaching us, offering a window into an epoch when galaxies were younger and more violent. Yet by the time we detect it, the actual event, the star torn apart, the black hole's feast has been over for millions or even billions of years. Each gamma-ray pulse is a postcard from the past, a reminder that the universe's most dramatic performances often play out on timescales beyond human comprehension. Blazars challenge our assumptions about the cosmos. They prove that even the most distant objects can dominate our skies, that destruction can illuminate as much as it obscures, and that the universe's most violent engines are also its most brilliant storytellers. Every flicker from these faraway monsters is a clue not just about the black holes powering them, but about the interconnected web of forces shaping the universe from its smallest particles to its grandest structures. The universe loves a good mystery, and gamma rays deliver some of the most baffling enigmas astronomers have ever encountered. While most high-energy photons trace back to known cosmic engines like black holes or colliding stars, some signals refuse to fit the mold. Take the case of gamma-ray flashes emerging from seemingly empty space regions where telescopes find no galaxies, no neutron stars, not even a wisp of gas to explain the outburst. These orphan gamma rays arrive without any obvious parent, leaving researchers scrambling for explanations. One theory suggests they could be the echoes of long-faded explosions, their original sources vanished but their light still reaching us across millennia. Another possibility, cosmic ghosts, high-energy particles interacting with interstellar magnetic fields in ways we don't yet understand. Then there are the rhythmic pulsars, gamma-ray sources that beat with the precision of a metronome. Unlike pulsars, whose steady ticks come from spinning neutron stars, these signals oscillate at intervals far too slow to be explained by stellar rotation. One particularly bizarre example, discovered in 2022, emits gamma-ray pulses every 18 minutes like clockwork. The object responsible doesn't match any known category. It's not dense enough to be a neutron star, not active enough to be a black hole, yet it's far too energetic to be an ordinary star. Some scientists speculate it could be a magnetar, a neutron star with an ultra-strong magnetic field, caught in a rare transitional state. Others wonder if we're seeing something entirely new, a previously unknown class of celestial object slowly revealing itself through these cryptic beats. The most tantalizing mysteries come from signals that seem almost intentional. In 2023, astronomers detected a series of gamma-ray bursts repeating in a mathematical pattern, not random, not naturally chaotic, but following a sequence that raised eyebrows. While the odds of this occurring naturally are slim, jumping to conclusions about alien technology would be premature. More likely, it's evidence of a cosmic process we haven't yet modeled, perhaps tied to the way matter accretes onto compact objects in tidal disruption events. Still, the discovery underscores how much we have yet to learn about the high-energy universe. These anomalies aren't just scientific curiosities, they're forcing physicists to revisit foundational assumptions. When gamma rays arrive with energies surpassing 100 trillion electron volts, they challenge the limits of Einstein's special relativity, probing whether light speed truly is the universe's ultimate speed limit. Other unexplained signals hint at exotic physics, like action-like particles or miniature black holes left over from the Big Bang. Each time an observation defies expectation, it opens new avenues for exploration, proving that even our best theories are works in progress. What makes these mysteries so compelling is their persistence. For every gamma-ray puzzle solved, another emerges, reminding us that the cosmos still holds cards close to its chest. Whether they're clues to undiscovered celestial phenomena, glimpses of new physics, or simply cosmic illusions we've yet to decipher, these enigmas keep astronomers on their toes and ensure that the story of gamma rays remains anything but predictable. Magnetic fields are the universe's invisible sculptors, bending and shaping gamma rays as they race across the cosmos. Unlike the straightforward pull of gravity, these fields twist and spiral through space, creating intricate pathways that high-energy particles must navigate. Nowhere is their influence more dramatic than in neutron stars, where magnetic fields reach strengths 1,000,000,000,000 times more intense than Earth's, so powerful they can rip atoms apart and whip electrons to near light speeds. In this extreme environment, charged particles spiral along magnetic field lines like cars on a cosmic roller coaster, gaining so much energy they emit gamma rays in brilliant, focused beams. Without these fields, the gamma-ray sky would be a shadow of itself, missing the pulsars, flares, and jets that define the high-energy universe. But neutron stars aren't the only places where magnetism rules. Supermassive black holes also harness magnetic fields to launch their jets, threading particles into narrow streams that stretch for millions of light years. These fields act like cosmic railguns, accelerating matter to velocities so extreme the jets glow in gamma rays visible across the universe. Even the turbulent regions around star-forming nebulae rely on magnetism to channel energy, stirring up gas and dust into the dense knots that collapse into new stars. It's a delicate balance: too strong a field and star formation stalls, too weak and matter never clumps together. Perhaps the most astonishing role of magnetic fields lies in their ability to store and release energy over cosmic timescales. When neutron stars collide or black holes merge, their magnetic fields become tangled and twisted, snapping like overstretched rubber bands. This sudden release powers some of the brightest gamma-ray flashes we observe, transforming stored magnetic energy into light. Even the diffuse gas between galaxies is threaded with faint magnetic fields, guiding cosmic rays and influencing how gamma rays travel through intergalactic space. Without these invisible threads, the universe's most energetic particles would scatter chaotically, their messages lost in the void. What makes magnetic fields so fascinating is their duality. They're both architects and destroyers. They shape the birth of stars and planets, yet they also rip matter apart in the hearts of black holes. They're the reason gamma rays arrive at Earth in focused beams instead of random noise, allowing us to trace their origins back to distant explosions and collisions. In the grand story of cosmic rebirth, magnetism is the silent force stitching together destruction and creation, proving that even the unseen can leave an indelible mark on the universe. Gamma rays aren't just cosmic destroyers, they're the universe's unlikely gardeners, scattering the seeds of life across the void. Every time a massive star explodes or neutron stars collide, the resulting gamma-ray burst does more than light up the cosmos it forges and flings the very elements that make biology possible. Carbon, oxygen, nitrogen, and iron are all cooked in these stellar furnaces, then blasted into space by the shockwaves of destruction. The gold in your ring, the calcium in your bones, even the oxygen you're breathing right now, all were forged in the heart of a dying star and distributed by the same violent events that light up the gamma-ray sky. Consider the aftermath of a supernova. As the shockwave expands, it rams into surrounding gas clouds, compressing them and triggering new star formation. Those newborn stars inherit a rich chemical legacy, heavy elements from the explosion swirling into their protoplanetary disks. Over billions of years, these disks coalesce into planets, some with just the right mix of ingredients to nurture life. Earth itself is a product of this cycle. Its oceans and atmosphere built from stardust delivered by generations of stellar explosions. Without gamma-ray bursts and supernova enriching the cosmos, our planet might still be a barren rock, devoid of the complexity that makes biology possible. Yet there's a razor's edge at play here. While distant gamma-ray bursts seed the universe with life's building blocks, a burst too close could erase life entirely. A strike within a few thousand light-years would bathe Earth in radiation powerful enough to strip away the ozone layer, exposing the surface to deadly ultraviolet light for years. Paleontologists have even speculated that a nearby burst might explain some of Earth's mass extinctions, moments when life's grip on the planet nearly slipped. It's a chilling paradox. The same phenomenon that supplies life's raw materials could also snuff it out in an instant. The deeper irony lies in timing. Gamma-ray bursts were far more common in the universe's youth, when massive stars formed and died in rapid succession. Back then, the cosmos was constantly sterilized by these explosions, yet it was also being flooded with the elements needed for life's eventual emergence. As the universe aged and gamma-ray bursts became rarer, the balance shifted. The heavy elements remained, but the sterilizing blasts grew infrequent enough for life to gain a foothold. We might owe our existence to this cosmic coincidence, a universe old enough to be chemically rich, but quiet enough to let that chemistry flourish. Astrobiologists now look for gamma-ray bursts in distant galaxies as clues to life's potential elsewhere. A galaxy with too many bursts might be a biological dead zone, its planets scoured clean before life can take hold. Another, with just the right number, could be a nursery for civilizations. By mapping these explosions across cosmic time, scientists are piecing together a grand story, one where destruction and creation are locked in a delicate dance, and where gamma rays serve as both the universe's wrecking ball and its paintbrush, tearing down old worlds while sketching the outlines of new ones. Far from being mere harbingers of chaos, these high-energy photons are silent partners in life's cosmic journey, etching the conditions for biology into the fabric of space itself. The next generation of gamma-ray telescopes is poised to revolutionize our understanding of the universe's most violent and enigmatic processes. Leading this charge is the Cherenkov Telescope Array, or CTA, an ambitious network of over 100 telescopes spread across 2 continents. Unlike traditional gamma-ray observatories that rely on satellites, the CTA detects the faint blue flashes created when gamma rays strike Earth's atmosphere, a phenomenon called Cherenkov radiation. This groundbreaking approach allows it to capture gamma rays with 10 times the sensitivity of current instruments, revealing details about black hole jets, neutron star collisions, and dark matter that were previously invisible. But the CTA isn't alone in pushing the boundaries. NASA's upcoming Compton Spectrometer and Imager, or COSI, will launch into orbit with a singular focus, mapping the gamma-ray sky in unprecedented detail. Specializing in lower-energy gamma rays, COSI will trace the formation of elements like aluminum and titanium in supernova remnants, offering new insights into how stars seed the universe with the building blocks of planets and life. Meanwhile, the European Space Agency's Advanced Telescope for High-Energy Astrophysics, Athena, will combine X-ray and gamma-ray observations to study the superheated gas swirling around black holes, probing how these monsters shape their host galaxies over cosmic time. What makes these missions so exciting isn't just their technological prowess, it's the mysteries they're designed to tackle. The CTA could finally settle the debate over dark matter by hunting for gamma-ray signatures from hypothetical particles like WIMP or actions. If these particles collide and annihilate in dense regions like galaxy clusters, the resulting gamma rays would carry a distinct energy signature. Similarly, COSI precision measurements might uncover the origins of positrons' antimatter particles that mysteriously abound near the Milky Way center. Are they produced by dark matter or by something even more exotic, like miniature black holes left over from the Big Bang? Perhaps the most tantalizing prospect lies in peering further back in time than ever before. Gamma rays from the early universe are incredibly faint by the time they reach us, but next-generation telescopes could detect the remnants of the very first supernova explosions that lit up the cosmos when it was less than 1 billion years old. These primordial bursts would reveal how the first stars lived and died, enriching the universe with its first heavy elements. Some theories even suggest we might catch gamma-ray echoes from cosmic inflation, the rapid expansion of spacetime moments after the Big Bang. Such a discovery would rewrite our understanding of the universe's birth, yet the true power of these missions lies in their ability to work together. When the SETI spots a fleeting gamma-ray burst, satellites like COSI can pivot to study its afterglow across multiple wavelengths. Gravitational wave detectors can simultaneously pinpoint the ripples in spacetime from merging neutron stars, while optical telescopes analyze the visible light. This multi-messenger approach combining gamma rays, gravitational waves, and traditional astronomy creates a three-dimensional picture of cosmic events, turning what were once blurry snapshots into high-definition movies of the universe's most dramatic moments. The data pouring in from these telescopes won't just answer existing questions, it will spark entirely new ones. Every time humanity has built a more sensitive gamma-ray observatory, we've stumbled upon phenomena that defy explanation. Pulsars spinning faster than physics should allow, gamma-ray flashes with no obvious source, or particles accelerated to energies that challenge Einstein's theories. The coming decade promises even more surprises as these cutting-edge instruments peel back another layer of the cosmic onion. One thing is certain, the universe's blueprint of rebirth, written in gamma-ray light, is about to come into sharper focus than ever before. Gamma rays have become a staple of science fiction, often portrayed as a mysterious force capable of transforming ordinary humans into superpowered beings or unleashing world-ending catastrophes. Think of the Incredible Hulk, whose origin story hinges on a gamma-ray experiment gone wrong, or the apocalyptic scenarios where gamma-ray bursts sterilize planets in a flash. These dramatic portrayals capture the imagination, but they barely scratch the surface of what gamma rays truly represent in the cosmos. The reality is far more fascinating and far less about green-skinned heroes. In truth, gamma rays are the universe's most energetic form of light, born from events so violent they defy human scale. While Hollywood leans on them as plot devices, real gamma-ray science reveals processes that sound like they're ripped from the pages of a cosmic thriller. Take colliding neutron stars. A single merger can unleash a fireball of gamma rays so intense it outshines entire galaxies for a fleeting moment. Or consider supermassive black holes, whose jets of high-energy particles stretch across millions of light-years, acting like natural particle accelerators dwarfing anything we could build on Earth. These phenomena don't just mutate fictional characters, they shape the very fabric of the universe, forging elements powering galaxies, and even influencing the potential for life itself. The gap between fiction and reality isn't just about scale, it's about wonder. While comic books reduce gamma rays to a convenient trope, astrophysicists see them as cosmic messengers, carrying secrets from the most extreme environments in existence. Every gamma-ray burst recorded by telescopes like Fermi is a snapshot of a universe in flux, a star's death cry, a black hole's feast, or the birth of elements we rely on every day. Unlike the simplified versions on screen, these real events are messy, unpredictable, and infinitely more complex. A gamma-ray burst doesn't just create a hero or destroy a planet, it seeds the cosmos with the ingredients for new stars, new worlds, and maybe even new life. Yet the allure of gamma rays in pop culture isn't entirely misplaced. Their destructive potential is real. A nearby burst could strip Earth's ozone layer, triggering mass extinctions. The difference is that these catastrophes unfold over millennia, not in the span of a 2-hour movie. And while gamma rays won't give you super strength, they do something equally extraordinary. They illuminate the invisible. Without gamma-ray astronomy, we'd be blind to the universe's most violent and creative acts. from the collisions that forge gold to the dark matter annihilations that might hold the key to the cosmos's structure. Separating fact from fiction doesn't diminish the awe, it deepens it. The next time you see gamma rays used as a shortcut for superpowers or doomsday, remember the real story. It's not about mutation or destruction, it's about revelation. Every gamma-ray photon reaching Earth is a whisper from the edge of physics, a reminder that the universe's truths are often stranger and far more spectacular than anything we could invent. Gamma rays don't just carry messages from across the universe, they deliver them in real time, racing toward us at the ultimate speed limit of nature, the speed of light. At 300,000 kilometers per second, these high-energy photons cross cosmic distances so vast that the numbers themselves lose meaning. A gamma-ray burst erupting in a galaxy 5 billion light-years away may have occurred before Earth even formed, but its light arrives today precisely as it left its source, unchanged by the eons of travel. This instantaneous delivery transforms astronomers into cosmic historians, observing cataclysmic events as they unfolded, not as they appear after the delays that plague other forms of observation. Consider the implications. When a star collapses into a black hole halfway across the observable universe, the gamma rays from that explosion reach our telescopes at the same moment the gravitational waves do, despite originating from entirely different processes. The gamma rays come from the jets punching through the dying star's outer layers, while the gravitational waves ripple from the warping of spacetime itself as the black hole forms. Yet both arrive in sync, offering a multi-messenger snapshot of the event's violent physics. This simultaneity is only possible because gamma rays, like all light, obey the universe's strictest traffic law. Nothing outpaces them. This speed also makes gamma rays indispensable for rapid response astronomy. When satellites like Fermi detect a burst, the light has already traveled millions or billions of years, but the moment it's spotted, telescopes worldwide can pivot to study the afterglow in visible light, X-rays, and radio waves. Without gamma rays' near instantaneous arrival, coordinating these observations would be impossible. It's like catching a flash of lightning and immediately training every camera in the world on the spot where thunder will rumble seconds later. The gamma-ray signal is the lightning, and everything else the fading afterglow, the elemental debris, even the gravitational wave echoes is the thunder trailing just behind. Yet this speed comes with a cosmic irony. While gamma rays deliver their messages without delay, interpreting those messages often takes years. A single burst might last just seconds, but unraveling its origins, whether it came from a collapsing star, merging neutron stars, or some unknown phenomenon, requires painstaking analysis of the light's energy spectrum, polarization, and aftereffects. The universe's fastest messengers demand our slowest, most careful scrutiny. What's truly remarkable is how this speed bridges the past and present. Every gamma-ray photon striking a telescope today is a frozen moment from deep cosmic history, a snapshot of conditions when the universe was younger, hotter, and more violent. By collecting enough of these snapshots, astronomers assemble a timeline of cosmic evolution, watching how stellar deaths, black hole births, and galaxy-shaping explosions have changed over billions of years. Gamma rays don't just show us the universe as it is, they reveal how it grew up, one light-speed flash at a time. What if the gamma rays streaming across the cosmos aren't just from our universe, but from others? The idea sounds like science fiction, but some physicists suspect these high-energy photons could carry whispers from parallel realities. Among the most tantalizing possibilities is that certain gamma-ray anomalies, flashes with unexplained energies or patterns, might be cosmic debris leaking through cracks in spacetime, evidence of neighboring universes brushing against our own. While firmly in the realm of speculation, the notion has gained traction as researchers grapple with gamma-ray signals that defy conventional explanations. Take the case of certain ultra-high-energy gamma rays, detected with energies so extreme they shouldn't survive the journey across interstellar space. According to known physics, these photons should collide with lower-energy light from the cosmic microwave background, losing energy long before reaching Earth. Yet here they are, arriving with unexplained vigor. One radical hypothesis suggests these outliers might be refugees from a neighboring universe with slightly different physical constants, one where the speed of light is marginally faster, or where particle interactions don't dampen high-energy photons as efficiently. If true, these gamma rays would be the first tangible evidence of a multiverse, a revelation that would upend our understanding of cosmic origins. The multiverse theory itself isn't new. Some versions arise from inflationary cosmology, suggesting our universe is one bubble among countless others in an endless cosmic foam. Others stem from string theory, where higher dimensional membranes, or branes, could oscillate near our own, occasionally exchanging energy. Gamma rays offer a unique way to test these ideas because their extreme energies make them sensitive probes of spacetime structure. A collision between universes might leave scars in the gamma ray background, subtle fingerprints in the form of directional hotspots or unusual spectral bumps. Telescopes like the Cherenkov Array are now scanning for these anomalies, treating the gamma-ray sky as a cosmic message board where parallel realities might have scrawled their presence. Even more intriguing are the theoretical models where gamma rays play a direct role in multiverse dynamics. In some scenarios, the birth of a new universe, a baby bubble in the multiverse, could release a burst of high-energy radiation detectable in our own cosmos. These signals would carry distinct signatures, like abrupt cutoffs in energy or polarization patterns impossible to replicate with known astrophysical sources. While no such smoking gun has been found, the search has already pushed detector technology to new limits, forcing scientists to reconsider what's possible. Skeptics rightly point out the challenges. Multiverse theories are notoriously difficult to test, often bordering on philosophy rather than empirical science. Gamma-ray anomalies could easily stem from mundane astrophysics we simply don't yet understand: unmodeled black hole behavior, exotic neutron star states, or even instrumental noise. But the very act of investigating these possibilities has value. Whether or not parallel universes exist, the quest to rule them out has led to sharper questions about gamma-ray origins, tighter constraints on particle physics, and even new methods for analyzing cosmic data. What makes this pursuit so compelling is its audacity. Gamma rays, long seen as messengers of stellar explosions and black hole jets, might also be our first lens into realities beyond our own. If even one anomalous flash turns out to be a multiverse ripple, it would rewrite not just astrophysics, but our place in the grand scheme of existence. Until then, every unexplained gamma-ray signal carries a thrilling question. Are we seeing the ordinary violence of our universe, or the first faint echoes of another? Leaving Earth's protective atmosphere means stepping into a cosmic shooting gallery, where gamma rays and other high-energy particles streak through space at nearly light speed. For astronauts on the International Space Station, Earth's magnetic field still offers some shelter, deflecting the worst of this radiation, but a journey to Mars. That's a different story. The 6 to 9 month trip through deep space would expose crews to gamma-ray levels hundreds of times higher than on Earth, equivalent to getting a full-body CT scan every few days. Even on the Martian surface, where the thin atmosphere provides minimal shielding, prolonged stays could risk cancer, cataracts, and even cognitive damage from particle impacts tearing through delicate brain tissue. The challenge isn't just about blocking gamma rays, it's about doing so without turning spacecraft into impossibly heavy fortresses. Traditional shielding like lead or concrete would require enormous mass, making launches prohibitively expensive. Scientists are exploring ingenious alternatives, water-filled walls that double as radiation barriers, since hydrogen atoms excel at scattering high-energy particles. Some propose lining habitats with polyethylene, a plastic rich in hydrogen, or even harvesting Martian soil to bury living modules under meters of regolith. The most futuristic ideas involve magnetic force fields, miniature versions of Earth's magnetosphere, that could deflect charged particles before they reach the hull. Yet the real wild card comes from gamma-ray bursts. While rare, a nearby burst during a Mars mission could deliver a lethal dose in seconds. Early warning systems are critical. Satellites like Fermi could alert crews to take cover in shielded compartments if a distant star's death throws light up the sky. Some designs suggest storm shelters lined with lithium hydride, a compound that absorbs gamma rays exceptionally well. But the ultimate solution might lie in speed, developing propulsion systems that slash travel time, reducing exposure windows. Nuclear thermal rockets or even experimental antimatter drives could one day make the Mars trip a matter of weeks instead of months. What makes this puzzle so urgent is the bigger picture. Beyond Mars, ambitions like lunar bases or asteroid mining demand long-term exposure solutions. And there's an ironic twist: the same gamma rays that threaten astronauts also carry clues about the universe's rebirth. Future deep space explorers might witness neutron star collisions or black hole eruptions firsthand, their shielded craft doubling as observatories. Imagine a crew on Europa's ice-covered ocean, protected by kilometers of ice while studying gamma-ray flashes from distant supernova, each burst a reminder that the universe's most destructive forces are also its most creative. The quest for gamma-ray protection isn't just about survival, it's about unlocking humanity's future as a spacefaring species. Every innovation in shielding brings us closer to the day when we're not just observers of cosmic rebirth, but active participants in the next chapter of the universe's story. Near the event horizon of a black hole, time itself warps into something unrecognizable, a phenomenon Einstein predicted over a century ago, now confirmed by the behavior of gamma rays. Imagine a photon of gamma-ray light escaping the gravitational jaws of a black hole, fighting against spacetime so distorted that every second for the photon stretches into years for an outside observer. This extreme time dilation isn't science fiction. It's a daily reality for gamma rays born in the universe's most violent neighborhoods. As these high-energy photons climb out of a black hole's gravity well, their light is stretched and their ticking slows, offering scientists a rare chance to test relativity under conditions no lab could ever replicate. The most striking evidence comes from active galaxies, where supermassive black holes spew jets of gamma rays across the cosmos. Observations reveal that these jets flicker in slow motion from our vantage point, their rapid flares appearing to drag on as if the universe itself had hit a pause button. In one famous case, a gamma-ray flare near the black hole at the center of galaxy M87 was clocked moving at apparent speeds faster than light, an illusion caused by the jet's material racing toward us at nearly light speed while battling extreme time dilation. These observations don't just confirm Einstein's theories, they push them to the breaking point, probing whether relativity holds true even when gravity bends time like taffy. But gamma rays don't just reveal time dilation, they turn it into a cosmic tool. By comparing the arrival times of gamma-ray photons with different energies, astronomers can reconstruct the gravitational environment around black holes. Lower energy photons, which take slightly longer to escape, lag behind their higher energy counterparts like runners staggered in a race. These minute delays, measured with nanosecond precision, map the warping of spacetime itself, revealing details about a black hole's mass, spin, and even the shape of its event horizon. It's as if each gamma-ray photon carries a tiny stopwatch, recording how long it spent fighting its way through the universe's most twisted gravity. The implications stretch far beyond black holes. Gamma-ray bursts from the early universe, their light stretched by cosmic expansion, also bear the fingerprints of time dilation. A burst lasting 20 seconds in its home galaxy might appear drawn out to minutes or hours by the time it reaches us, its ticking slowed by the expanding fabric of space. This cosmic time stretching helps astronomers measure the universe's expansion rate and even probe the nature of dark energy, the mysterious force accelerating that expansion. What's truly humbling is realizing that every gamma-ray signal reaching Earth is a time traveler, some from epochs when galaxies were just forming, others from black holes where time crawls to a near standstill. These photons don't just cross space, they carry snapshots of how time itself behaves under extremes no human will ever experience firsthand. In their silent journey, they reveal a universe far stranger than Einstein ever imagined, one where time is not a constant river, but a twisting, turning vortex shaped by gravity, motion, and the very structure of reality. Look up at the night sky with just your eyes, and it seems serene, a scattering of stars against an inky black canvas. But point a gamma-ray telescope in any direction, and that calm vanishes. The entire cosmos hums with a faint, persistent glow, like the static between radio stations. This gamma-ray background isn't random noise. It's the cumulative whisper of every explosion, collision, and cataclysm the universe has ever produced, all overlapping into a cosmic chorus. Somewhere in that haze are the echoes of supernova too distant to spot individually, the fading screams of black holes that flared and vanished billions of years ago, and perhaps even relics from the universe's first violent seconds. Deciphering this glow is like trying to isolate individual voices in a stadium crowd. Take the Fermi Gamma-Ray Space Telescope's maps. They reveal a sky crisscrossed by bright sources like pulsars and blazars, but between them lies a diffuse fog that defies simple explanation. Part of it comes from countless unresolved gamma-ray bursts, their afterglows blended into a uniform shimmer. Another fraction arises from cosmic rays' high-energy protons slamming into interstellar gas, creating pions that decay into gamma rays. Then there's the possibility of more exotic contributors, like dark matter particles annihilating in the voids between galaxies, or primordial black holes evaporating in bursts of Hawking radiation. What makes this background so valuable is its archival quality. Just as archaeologists sift through layers of sediment to reconstruct ancient ecosystems, astronomers dissect the gamma-ray fog's energy spectrum to piece together cosmic history. Certain energy signatures hint at epochs when star formation peaked, flooding the universe with supernova. Others might trace the heyday of quasar activity, when young galaxies' black holes gorged on gas and lit up the cosmos. There's even a chance the faintest, highest energy photons could be relics from the Big Bang itself, stretched and diluted but still carrying whispers of creation. The real frontier lies in teasing apart these signals. New analysis techniques, like machine learning algorithms trained to recognize subtle spectral patterns, are beginning to isolate individual contributors. Imagine identifying the gamma-ray voice of a population of ancient neutron stars too faint to see directly, or detecting the collective glow of thousands of microscopic black holes left over from the universe's birth. Some theorists even propose that certain anomalies in the background could point to entirely new physics, extra dimensions, cosmic strings, or particles beyond the standard model. Yet the gamma-ray background's greatest gift might be its incompleteness. Like a half-decoded ancient manuscript, its ambiguities force scientists to ask better questions. Why does the fog's intensity drop off at certain energies? What causes those faint, unexplained fluctuations in its distribution? Every discrepancy is a clue, hinting at cosmic phenomena we've yet to imagine. In the end, this ubiquitous glow isn't just noise, it's the universe's collective memory, written in light we're only just learning to read. Gamma rays don't just push the boundaries of energy, they shatter our understanding of reality itself. At these extreme energies, the familiar rules of classical physics dissolve, and the bizarre world of quantum mechanics takes over. Particles that should be predictable start behaving in ways that defy logic, appearing in two places at once or influencing each other instantaneously across vast distances. This isn't just theoretical speculation. Gamma-ray observations have caught particles in the act of breaking the rules, forcing scientists to rethink the very foundations of physics. Take gamma-ray bursts, for example. When particles in these jets accelerate to near-light speeds, they emit photons with energies so high that quantum effects can't be ignored. Under normal circumstances, light travels in straight lines, but near a black hole or neutron star, gamma rays can twist and bend in ways that suggest spacetime itself is frothing with quantum fluctuations. Some theories propose that at these energies, space isn't smooth and continuous but granular, like a cosmic foam where tiny wormholes blink in and out of existence. Gamma rays might be slipping through these microscopic shortcuts, arriving at Earth with properties that challenge Einstein's relativity. Then there's the mystery of particle entanglement, a quantum phenomenon where two particles remain mysteriously linked no matter how far apart they are. In gamma-ray jets, particles born from the same violent event could stay entangled even as they race across the cosmos. If scientists could measure these connections, say, by comparing the polarization of gamma rays from opposite sides of a jet, it might reveal whether quantum weirdness persists over astronomical distances. Such a discovery could bridge the gap between quantum mechanics and gravity, two realms of physics that have stubbornly refused to unite under a single theory. The Holy Grail here is a theory of quantum gravity, a framework that explains how the universe behaves at both the smallest and largest scales. Right now, general relativity handles the cosmos beautifully, while quantum mechanics excels at explaining subatomic particles. But where gamma rays are born, these two theories collide in spectacular disagreement. Black holes are the ultimate testing ground. Their immense gravity warps spacetime, yet their tiny size demands a quantum description. Gamma rays escaping from near their event horizons carry imprints of this battle, offering clues about how gravity might emerge from quantum interactions. What makes gamma rays so invaluable is their ability to probe energies unreachable in any lab. The Large Hadron Collider can smash particles together at tremendous speeds, but even it can't match the petaelectronvolt energies seen in some cosmic gamma rays. Nature, it seems, is the ultimate particle accelerator, and gamma-ray telescopes are our front-row seats to its most extreme experiments. Every unexplained gamma-ray anomaly, whether it's an unexpected energy spike or a particle moving just a fraction too fast, could be a hint of new physics, a sign that there's more to the universe than our current theories allow. The implications stretch far beyond astrophysics. If gamma rays help unlock quantum gravity, it wouldn't just solve a cosmic mystery, it could revolutionize technology. Imagine harnessing quantum entangled gamma rays for unhackable interstellar communication, or tapping into the energy of virtual particles that flicker at the edge of spacetime. More fundamentally, it would rewrite our story of cosmic rebirth, showing how the universe's largest structures, galaxies, black holes, even the fabric of spacetime itself, might arise from the tiniest quantum seeds. In the end, gamma rays are more than cosmic messengers, they're bridges between worlds. Each photon carries the fingerprints of quantum chaos, a reminder that the universe's most violent rebirths might be written in a language we're only beginning to decipher. And as we piece together this quantum puzzle, we're not just observers of the cosmos, we're students of its deepest, most enigmatic laws. Our solar system might seem calm compared to the violent gamma-ray storms of distant galaxies, but don't be fooled. Even here, high-energy light crackles through the void. The Sun, our nearest star, occasionally erupts in solar flares so powerful they unleash gamma-ray bursts rivaling those from deep space. During these eruptions, magnetic fields on the Sun's surface twist and snap like overstretched rubber bands, accelerating particles to nearly light speed. When these particles collide with the Sun's dense plasma, they trigger nuclear reactions that emit gamma rays, the same processes that power hydrogen bombs, but on a cosmic scale. These solar gamma rays aren't just a spectacle. They're a natural laboratory, letting astronomers study particle acceleration and magnetic reconnection up close, with implications for understanding far more extreme events across the universe. Jupiter, the solar system's largest planet, offers another surprise. Its auroras glow not just in visible light, but in gamma rays too. Unlike Earth's northern lights, which are powered by solar wind particles interacting with our atmosphere, Jupiter's auroras draw energy from its own volcanic moon, Io. Sulfur and oxygen ions spewed by Io's eruptions get caught in Jupiter's monstrous magnetic field, which is 20,000 times stronger than Earth's. As these particles spiral toward Jupiter's poles, they smash into the upper atmosphere with enough force to generate gamma rays. The result, auroras so energetic they'd be lethal to humans, pulsing with gamma radiation visible to space telescopes like NASA's New Star. These displays aren't just beautiful, they're teaching scientists how magnetic fields channel and focus energy, a process that plays out on grander scales around pulsars and black holes. What makes these local gamma-ray sources so valuable is their role as cosmic yardsticks. Distant phenomena like blazar jets or colliding neutron stars are too far away to study in detail, but the Sun and Jupiter are right in our backyard. By analyzing how gamma rays are produced and scattered in our solar system, astronomers can fine-tune their models, ensuring that interpretations of far-off events are grounded in reality. For instance, solar flares reveal how magnetic turbulence generates gamma rays, a blueprint for understanding similar processes in the accretion disks of black holes. Jupiter's auroras, meanwhile, mimic the particle acceleration seen in Magnetar's neutron stars with magnetic fields a quadrillion times stronger than Earth's, but under conditions we can observe repeatedly and up close. There's also a practical side to studying these local gamma-ray factories. Solar storms powerful enough to produce gamma rays can disrupt satellites, power grids, and even astronaut safety. By monitoring the Sun's high-energy outbursts, scientists gain advance warning of space weather threats. Jupiter's gamma-ray auroras, on the other hand, serve as a testbed for theories about radiation belts and atmospheric chemistry, knowledge that could prove vital for future missions to icy moons like Europa, where similar processes might occur beneath the ice. The lesson here is profound. Gamma rays aren't just the domain of distant supernova or exotic black holes. They're woven into the fabric of our own celestial neighborhood, reminding us that the universe's most extreme physics operates even in familiar places. From the Sun's fury to Jupiter's radiant poles, these local phenomena are more than just curiosities, they're the keys to deciphering the cosmos. one high-energy photon at a time. Gamma rays might hold the key to unlocking one of cosmology's greatest mysteries, the moment the universe exploded from subatomic size to cosmic vastness in a fraction of a second. This runaway expansion, known as cosmic inflation, is thought to have occurred just moments after the Big Bang, smoothing the universe into the uniform tapestry we see today. But how could gamma rays, typically associated with black holes and dying stars, possibly reveal secrets from this primordial epoch? The answer lies in the faint afterglow of inflation itself, a signal etched into the fabric of spacetime that gamma-ray telescopes are uniquely equipped to trace. According to leading theories, inflation wasn't perfectly smooth. Quantum fluctuations during this rapid stretching of space left behind tiny ripples, variations in density that eventually seeded the formation of galaxies and galaxy clusters. These same ripples should have also generated a background of gravitational waves, subtle vibrations in spacetime that persist to this day. While these waves are too faint to detect directly, their presence could be imprinted on the cosmic microwave background, the afterglow of the Big Bang. Here's where gamma rays enter the picture. If inflation's gravitational waves interacted with the early universe's magnetic fields, they might have produced a distinct polarization pattern in the microwave background, one that could scatter or modulate certain gamma-ray signals. Telescopes hunting for these subtle distortions are essentially looking for cosmic fingerprints, evidence of inflation's violent birth throes. The stakes couldn't be higher. If gamma-ray observations confirm inflationary patterns, it would validate a cornerstone of modern cosmology, explaining why the universe appears so uniform on large scales. More tantalizingly, it could reveal whether inflation was a one-time event or part of a cyclical process, a series of cosmic rebirths where universes expand, cool, and collapse in an endless cycle. Some models even suggest that gamma-ray anomalies, like unexplained spectral bumps or directional hotspots, could be echoes of collisions between our universe and others in a vast multiverse. These ideas remain speculative, but the mere possibility underscores how gamma rays bridge the gap between the universe's earliest moments and its present-day structure. What makes this search so challenging is the sheer faintness of the signal. Inflation's imprint would be buried under eons of later cosmic noise, supernova remnants, black hole jets, and other gamma-ray sources. Separating the primordial whisper from the astrophysical cacophony requires instruments of exquisite sensitivity, like the next-generation Cherenkov telescope array or space-based observatories designed to map the gamma-ray sky with unprecedented precision. Even then, the signal might be indirect, hidden in statistical patterns or correlations that only emerge after years of painstaking data collection. Yet the potential payoff justifies the effort. Gamma rays could do more than confirm inflation. They might reveal its energy scale, whether it was driven by a single quantum field or a cascade of exotic particles, even how hot the universe was when inflation ended. These details would transform inflation from a compelling idea into a detailed history, filling in the blank pages of the universe's first moments. And if the data defies expectations, that would be equally revolutionary, forcing physicists to reconsider whether inflation happened at all, or if the cosmos was born through some even more extraordinary mechanism. In the end, gamma rays offer something rare in science, a direct line to the universe's birth. Every photon carrying the faintest hint of inflationary patterns is a messenger from a time before time, a glimpse into the instant when the entire cosmos was smaller than a single atom. Whether they confirm our theories or upend them, one thing is certain: the story of cosmic inflation is still being written, and gamma rays are holding the pen. Deep within meteorites, those ancient fragments of rock drifting through space, lies a hidden clock, ticking away with the precision of atomic decay. These cosmic timepieces don't rely on gears or springs, but on the steady breakdown of radioactive elements like aluminum-26 and iron-60. As these isotopes decay, they emit gamma rays at rates so consistent they've become the universe's most reliable chronometers. When scientists crack open a meteorite and measure these gamma-ray signatures, they're not just analyzing rock, they're reading a timeline that stretches back over 4.5 billion years, to the very moment our solar system coalesced from a swirling cloud of dust and gas. Take the case of the Alend meteorite, a carbonaceous chondrite that fell to Earth in 1969. Inside its rugged exterior, researchers found traces of magnesium-26, the decay product of aluminum-26. By comparing the ratios of these isotopes, they pinpointed the meteorite's formation to within a stunningly narrow window, just a few million years after the solar system's birth. That's like determining the exact minute a candle was lit by studying the wax strips left behind. The gamma rays emitted during this decay process act as atomic stopwatches, freezing a moment in time that predates the Earth itself. This technique isn't limited to meteorites. Lunar samples brought back by Apollo astronauts reveal similar gamma-ray fingerprints, helping reconstruct the Moon's violent origins. The prevailing theory suggests a Mars-sized body, Theia, slammed into the young Earth, ejecting debris that eventually formed the Moon. Gamma-ray measurements of lunar rocks show their composition matches Earth's mantle, but with subtle differences that align exactly with the timing of this colossal impact. Without gamma-ray chronometry, this story would remain speculative. Instead, it's a chapter written in the language of radioactive decay, etched into rock and light. Beyond our solar system, gamma rays serve as cosmic hourglasses for even grander processes. In supernova remnants like Cassiopeia A, the decay of titanium-44, a radioactive isotope forged in the explosion, produces gamma rays that let astronomers track the blast's expansion over centuries. By observing how these gamma-ray signals fade, scientists can reconstruct the supernova's energy and even estimate when the progenitor star died. It's forensic astronomy, using high-energy photons to piece together stellar crime scenes from millennia ago. What makes gamma-ray clocks so extraordinary is their universality. Whether in a speck of interstellar dust or the aftermath of a dying star, radioactive decay follows the same immutable laws. This consistency allows researchers to compare timelines across the cosmos, synchronizing events from the solar system's infancy to the deaths of distant suns. Every gamma-ray photon carries not just energy but history, a whisper from the past that helps us measure the universe's age, track its evolution, and even predict its future. Yet these clocks are more than just scientific tools, they're reminders of our cosmic connectedness. The same radioactive elements that power gamma-ray chronometers also heated the early Earth, driving the geologic processes that shaped continents and oceans. They're the reason our planet's core remains molten, fueling the magnetic field that protects life from solar storms. In a very real sense, the gamma rays we measure today are echoes of the forces that made our world habitable, linking the birth of atoms to the rise of biology. As technology advances, so too does our ability to read these atomic timelines. Future missions may deploy gamma-ray spectrometers on asteroids or Mars, unlocking even finer details of the solar system's chaotic youth. Each new measurement sharpens the picture, turning vague estimates into precise milestones. The universe, it seems, keeps perfect time. We're just learning to listen to its rhythm. Gamma rays might be the universe's ultimate calling card, not just natural phenomena, but potential signals from civilizations far beyond our own. Imagine an advanced society, millions of years ahead of us, needing a way to broadcast their presence across the cosmos. Radio waves, the traditional focus of SETI, could seem quaint to them like smoke signals in the age of the internet. But gamma rays, these high-energy photons cut through interstellar noise like a laser through fog, carrying messages that could span galaxies without fading into the background hum of the universe. SETI, the search for extraterrestrial intelligence, has long listened for radio pulses or laser flashes. But in recent years, they've expanded their hunt to include gamma-ray patterns that defy natural explanations. The logic is simple. A gamma-ray burst engineered by intelligence wouldn't behave like a random stellar explosion. It might repeat at precise intervals, encode mathematical sequences in its energy spectrum, or arrive from a point in space devoid of known gamma-ray sources. In 2022, researchers even proposed looking for gamma-ray lighthouses, artificial beams swept across the galaxy like a cosmic beacon, designed to catch the attention of emerging civilizations. The idea isn't as far-fetched as it sounds. Humanity already uses gamma rays for practical purposes: medical imaging, cancer treatment, even spacecraft propulsion concepts. A civilization with mastery over stellar-scale energy could theoretically harness gamma rays to power interstellar travel or transmit information. Picture a Dyson swarm, a fleet of energy collecting satellites around a star, redirecting a fraction of that power into focused gamma-ray pulses. Such a signal could outshine a star for nanoseconds, just long enough to stand out against the cosmic background while conserving energy. Yet the challenges are immense. Natural gamma-ray sources are so varied and energetic that distinguishing an artificial signal would require extraordinary evidence. A repeating pattern might suggest intelligence until you discover it's a previously unknown type of pulsar. An unusually narrow beam could hint at engineering until simulations show black hole jets can produce similar collimation. SETI scientists must rule out every natural explanation before whispering the word alien. But the search itself is transformative. Even if we never find gamma-ray greetings, the effort pushes technology forward. Detecting subtle patterns in gamma-ray data requires algorithms capable of sifting through noise with unprecedented precision, tools that also enhance our understanding of astrophysical processes. And the philosophical implications linger. If a civilization can manipulate gamma rays, what else might they control? Mastery over such energy suggests knowledge of physics we've yet to dream of, from taming black holes to warping spacetime itself. Perhaps the most tantalizing thought isn't whether gamma rays carry messages, but what they might say. A signal lasting microseconds could contain more information than all of human history, compressed into bursts of light. Decoding it would be like finding an encyclopedia written in lightning, each flash a chapter in an alien saga. Until then, every unexplained gamma-ray flicker holds a question. Are we alone, or is the universe humming with conversations we're just beginning to hear? When two neutron stars spiral toward catastrophe or black holes circle each other in a final, furious dance, they don't just shake the cosmos, they scream in gamma rays and whisper in gravitational waves. These two signals, born from the same cataclysm but traveling through entirely different channels, give us something unprecedented, a multi-sensory window into the universe's most violent rebirths. Gravitational waves, ripples in spacetime itself, carry the bass notes of the collision, the masses of the objects, their spins, the final moments before merger. Gamma rays, meanwhile, deliver the high-energy crescendo, the explosive aftermath where matter is vaporized, magnetic fields snap, and particles are accelerated to unfathomable speeds. Together, they transform astrophysics from a silent movie into an IMAX experience with surround sound. The breakthrough came in 2017 with the collision of two neutron stars, an event dubbed GW170817 after the gravitational wave signal that announced its arrival. 2 seconds after those ripples reached Earth, the Fermi Gamma-Ray Space Telescope caught a short gamma-ray burst flashing from the same patch of sky. That precise timing was the smoking gun, a proof that these mergers aren't just theoretical curiosities but real cosmic factories, forging heavy elements and powering some of the brightest flashes in the universe. Telescopes across the planet swiveled to observe the aftermath, capturing the kilonova's glow in visible light, X-rays, and radio waves. For the first time, humanity had witnessed a cosmic catastrophe in every wavelength and dimension, from the warping of spacetime to the creation of gold and platinum in the debris. What makes this combination so powerful is how these signals complement each other. Gravitational waves pass cleanly through gas, dust, and even entire galaxies, arriving undistorted from the moment of merger itself. Gamma rays, though often absorbed or scattered, carry details about the environment surrounding the crash, the density of ejected material, the strength of magnetic fields, even the angle at which the explosion is directed. It's like piecing together a car accident by both feeling the impact and seeing the shattered glass. Gravitational waves tell us how the collision happened. Gamma rays show us what was left in its wake. The implications stretch far beyond neutron stars. When black holes merge, they typically don't produce gamma rays. No matter means no light. But in rare cases where they're surrounded by disks of gas, the gravitational waves can trigger shocks in that material, sparking gamma ray flares. These mixed events are cosmic Rosetta Stones, revealing how black holes interact with their environments. Similarly, hypothetical collisions involving exotic objects like quark stars or primordial black holes might leave unique signatures in both channels. Gravitational waves revealing their bizarre internal structure, gamma rays exposing their explosive interactions with normal matter. This synergy is pushing technology to its limits. Gravitational wave detectors like LIGO and Virgo are now fine-tuned to alert gamma-ray telescopes within seconds of a potential merger, allowing rapid scans of the sky. Future missions like the space-based LISA Gravitational Wave Observatory will extend this partnership to supermassive black holes, whose mergers are too low frequency for ground-based detectors but could produce gamma-ray fireworks lasting years. The DREAM is a real-time, all-wavelength observatory network, a cosmic surveillance system that catches every crash, flare, and rebirth as it happens. Yet the most profound revelation isn't technical, it's philosophical. For centuries, astronomy relied solely on light. Gravitational waves opened a new sense, letting us hear the universe. Combining these with gamma rays is like gaining synesthesia, where collisions become symphonies of spacetime and energy. A neutron-star merger isn't just an explosion. It's a process where gravity and light collaborate to scatter the elements of life across the cosmos. Every time these signals align, we're not just observers, we're witnesses to the universe's endless cycle of destruction and creation, rendered in perfect multidimensional clarity. Will the universe end in frozen silence or fiery rebirth? The answer might be written in gamma rays. The very same high-energy light that illuminates stellar explosions today could reveal our cosmos's ultimate fate. Current theories paint two starkly different endings: heat-death, where the universe expands forever until all energy dissipates into cold emptiness, or the Big Crunch, where gravity eventually reverses expansion, collapsing everything back into a singularity. But there's a third, more dramatic possibility: a cyclical universe, endlessly dying and being reborn like a cosmic phoenix. Gamma-ray observations might be our first clue to which path we're on. The key lies in dark energy, the mysterious force accelerating the universe's expansion. If this energy weakens over time, gravity could regain dominance, pulling galaxies back together in a cataclysmic collapse. Alternatively, if dark energy strengthens, it might eventually tear apart atoms themselves in a big rip. Gamma rays offer a way to track these changes. By studying how gamma ray bursts dim over cosmic distances, astronomers can measure whether the universe's expansion rate has shifted across billions of years. A surprising pattern, like bursts appearing brighter or fainter than expected at certain distances, could hint at dark energy's evolving strength, tipping the scales toward one apocalyptic scenario over another. Even more intriguing are hints of a cyclical universe. Some models suggest that each big crunch doesn't end the story. It births a new universe through a big bounce, with gamma rays from the previous cycle imprinting faint echoes onto the next. These echoes might appear as anomalies in the gamma ray background, subtle fluctuations that don't match known astrophysical sources. Other theories propose that colliding brain universes in higher dimensional space could release gamma ray signatures detectable in our sky, like cosmic bruises from a long-ago collision with another reality. The most tantalizing evidence might come from the universe's earliest moments. Gamma rays traveling since the Big Bang carry information about primordial conditions. If they reveal unexpected patterns like preferred directions or energy thresholds, it could suggest our universe isn't the first iteration. Imagine finding a gamma ray fingerprint repeating across the sky, a relic of a previous cosmic cycle encoded in high-energy light. Such a discovery would rewrite not just our future, but our past, revealing a cosmos that has lived many lives before this one. Yet the ultimate fate of the universe isn't just a question for telescopes, it's deeply personal. The same gamma rays that might herald cosmic rebirth are also the byproducts of the stellar explosions that forged the atoms in our bodies. We're made of star stuff, yes, but perhaps also of universe stuff, the ashes of prior cosmic cycles recycled into new form. Whether the story ends in ice, fire, or eternal return, gamma rays are the universe's way of keeping a diary, and we're only just learning to read its most profound entries. Gamma ray astronomy isn't just about collecting light, it's about solving a cosmic puzzle where half the pieces are missing and the rest are buried in static. Every second, telescopes like Fermi beam down torrents of raw data, a flood of ones and zeros that might contain the secrets of black holes, dark matter, or even the Big Bang. But sifting through this deluge is like trying to hear a whisper in a hurricane. The universe's most energetic light doesn't arrive cleanly. It's drowned in noise, cosmic rays from distant supernova, random flickers from Earth's own atmosphere, even false signals generated by the detectors themselves. Untangling this mess requires more than just powerful computers. It demands AI systems trained to recognize patterns no human eye could spot, running on supercomputers that crunch numbers faster than entire galaxies spin. Take the hunt for gamma-ray bursts, for example. These fleeting explosions can last anywhere from milliseconds to minutes, and missing one means losing a priceless snapshot of cosmic violence. To catch them, algorithms must scan the sky in real time, distinguishing true bursts from glitches caused by solar flares or passing satellites. It's a high-stakes game of cosmic, where's Waldo? Where Waldo might vanish before you blink. Even after a burst is identified, the real work begins reconstructing its energy spectrum, pinpointing its origin, and decoding what it reveals about the event that created it. This isn't just number crunching, it's digital archaeology, peeling back layers of interference to uncover the signal's true story. Then there's the challenge of false positives. The gamma-ray sky is littered with mirages, phantom signals that look like dark matter annihilations or new pulsars, but turn out to be statistical flukes. In 2019, researchers thought they'd found evidence of dark matter in the Milky Way's center, only to realize the excess gamma rays might just be a crowd of undiscovered neutron stars. Telling the difference requires painstaking simulations, modeling how every known gamma-ray source should behave and seeing where reality deviates. These simulations are so complex they can take months to run, pushing supercomputers to their limits as they virtually recreate chunks of the universe to compare against telescope data. But perhaps the greatest hurdle is sheer volume. Fermi alone has catalogued over 5,000 gamma-ray sources, each generating terabytes of data over its mission. Traditional analysis methods where scientists manually inspect signals are laughably inadequate for this scale. Instead, machine learning now does the heavy lifting, with neural networks trained to flag anomalies, classify sources, and even predict when a black hole might flare next. These AI tools don't replace human intuition, they amplify it, highlighting connections that might take years to spot otherwise. When the next neutron star collision lights up the gamma-ray sky, it won't just be humans watching, it'll be algorithms ready to decode the universe's blueprint faster than ever before. What makes these challenges worthwhile is their payoff. Every noise-filtered signal, every confirmed detection, adds a stroke to the masterpiece we're piecing together, a portrait of the universe written in gamma-ray light. The struggles of today are the breakthroughs of tomorrow, turning raw data into revelations about how stars die, how elements form, and how the cosmos continually reinvents itself. Behind every headline about a cosmic discovery, there's an unsung hero, the code, the hardware, and the minds that turned chaos into clarity. Gamma-ray astronomy isn't locked away in ivory towers. It's happening on home computers, tablets, and smartphones around the world, thanks to projects that turn everyday people into cosmic detectives. Take Gamma Hunters, a citizen science initiative where volunteers sift through real telescope data, flagging unusual gamma-ray signals that might slip past automated algorithms. One participant, a retired teacher in Portugal, spotted a faint pulse from a previously unknown neutron star. A high school student in Japan helped identify a blazar flare that professional astronomers had overlooked. These aren't isolated cases, they're proof that discovery doesn't always wear a lab coat. When thousands of eyes scan the gamma-ray sky together, patterns emerge that even the most advanced software might miss. What makes these projects revolutionary isn't just their scale, it's their accessibility. You don't need a PhD to recognize a gamma-ray burst's telltale spike or a pulsar's rhythmic flicker. Platforms like Zooniverse provide intuitive tutorials, guiding volunteers through real datasets from telescopes like Fermi. Some participants specialize in tracking ghost sources, gamma rays that appear and vanish without explanation. Others hunt for extended gamma-ray glows around galaxy clusters, potential signposts of dark matter. The collective effort creates a living map of the high-energy universe, annotated by curious minds from all walks of life. The impact goes beyond raw numbers. When citizen scientists uncover something new, a peculiar burst, a drifting source, they're often invited to co-author research papers. A 2021 study on orphan gamma-ray flares, those with no visible counterparts, listed over 50 amateur contributors alongside professional astronomers. This collaboration reshapes who gets to participate in cosmic storytelling. A farmer in Kenya, a nurse in Canada, and a software developer in India might all see their names in the same astrophysics journal, united by photons that traveled billions of years to reach them. But perhaps the most profound effect is how these projects reframe our relationship with the cosmos. gamma rays aren't just distant curiosities, they're threads in a shared human experience. Every time a volunteer tags a mysterious flash, they're touching the same raw data that might reveal a black hole's last meal or the birth of elements essential for life. It's science stripped of jargon, where the universe's grand cycles of destruction and rebirth become something you can explore during a coffee break. And in an era where algorithms dominate discovery, these initiatives remind us that human intuition, that gut feeling when something looks off, still plays a vital role in decoding the cosmos. The data deluge from next-generation telescopes will only deepen this partnership, as projects like the Cherenkov Telescope Array come online, generating petabytes of gamma-ray observations. The need for creative pattern recognition will explode. Citizen scientists might be the first to spot anomalies hinting at entirely new phenomena, perhaps a gamma-ray source blinking in Fibonacci sequences, or a particle interaction that defies known physics. In chasing these enigmas, we're not just mapping the universe, we're reclaiming the idea that its wonders belong to everyone, one click at a time. From stellar explosions to black hole jets, gamma rays trace the universe's endless cycle of death and rebirth. They're not just radiation, they're storytellers, revealing how chaos creates, how destruction builds. As new telescopes launch, we'll uncover even deeper truths. The next time you gaze at the stars, remember, their light is just the beginning. The real story is written in gamma rays, waiting to be read. Keep exploring, keep questioning, and let the cosmos amaze you. But this isn't just about distant celestial fireworks, it's about us too. Every atom heavier than iron in your body, from the calcium in your bones to the iodine in your thyroid, was forged in the heart of a dying star and scattered across space by the same gamma-ray explosions we've been studying. That gold ring on your finger, it was likely born in a neutron star collision, flung into the cosmos by a kilonova's fury billions of years ago. We're not just observers of this cosmic recycling program, we're products of it. Stardust shaped into sentience by the universe's relentless cycle of destruction and renewal. The beauty of gamma-ray astronomy lies in its ability to connect the unimaginably vast with the intimately personal. Those faint streaks of high-energy light aren't just data points, they're echoes of our origins. When a telescope catches a gamma-ray burst from a galaxy halfway across the observable universe, it's not just recording a cataclysm, it's capturing the same process that, eons ago and far away, seeded the raw materials for planets and life. The universe doesn't waste its tragedies, it transforms them into beginnings, and the story is far from over. With every technological leap, we peel back another layer of this cosmic onion. The Cherenkov Telescope Array will soon scan the sky with unprecedented precision, hunting for gamma-ray whispers from dark matter or the first stars. Space-based detectors like COSI will map the births of elements in real time, watching as supernova and neutron star mergers forge the building blocks of future worlds. Even now, citizen scientists combing through Fermi's data might stumble upon anomalies that rewrite textbooks, proof that discovery isn't reserved for elites with PhDs, but for anyone curious enough to look. So the next time you step outside on a clear night, don't just admire the stars, listen for the stories they're not telling. Behind their steady glow lies a hidden universe of violence and rebirth, written in gamma rays. Those invisible photons carry tales of black holes birthing galaxies, of stellar death seeding life, of a cosmos that reinvents itself with every collision and explosion. The night sky isn't a static painting, it's a living, breathing saga, and we're just beginning to learn its language. The adventure doesn't end here. every unanswered question, the nature of dark matter, the fate of the universe, the possibility of other life, is a new chapter waiting to be written. And with each passing year, our tools grow sharper, our understanding deeper. So stay curious. The universe has spent billions of years preparing its greatest secrets, and it's not about to reveal them all at once. But one thing's certain, the story of gamma rays is the story of everything, and it's far